Alright, so I'm going to work some of the problems from the inverted lecture 1, which was review material for from chemistry 255. Now the first question talks about drawing the highest and lowest energy conformation for 3-methylpentane as viewed down the carbon-2, carbon-3 bond. So 3-methylpentane would be this structure, and we would be looking down this bond. That would be the carbon-2, carbon-3 bond. And so I've built a model just to kind of show what we're dealing with here. So we're going to be looking down this bond of 3-methylpentane, and when we look down that bond down through here, you have to assign the sizes to the groups that are on each one of the carbons. So this is going to be my front carbon. I've got a methyl group, which is going to be my large group because the other two groups on this carbon are hydrogens. And then my back carbon is going to have a hydrogen, which of course is going to be the small group. I'm going to have a methyl group, which will be medium, and then I'll have a ethyl group, which is going to be my large group. Now we know that in the lowest energy conformation, the two large groups on the two carbons need to be 180 degrees apart from one another. And so in our lowest energy conformation, we're going to have our back carbon with an ethyl group, a methyl group, and a hydrogen attached to it. And our front carbon will have two hydrogens and a methyl group. And again, the methyl and the ethyl group on the back carbon need to be 180 degrees apart from one another. And so this is going to be the lowest energy conformation. Now, if we think about our highest energy conformation, I'm going to leave the back carbon exactly as it is. So I'll have the ethyl group coming up. I'll have my methyl group off to the side. I'll have my hydrogen. But I know that my front carbon, I'm going to have the big groups eclipsing one another. And the hydrogens are going to be eclipsing each other in the methyl group. And so in this total eclipse conformation, this is going to be the highest energy conformation that we can have there. Let's go on to question number 2, which talks about drawing reaction energy diagrams for the reaction of ethanol and acetic acid with potassium hydroxide, two separate reactions. And so if we think about these two reactions, these are nothing more than acid-base reactions. So if you take ethanol, which has one acidic hydrogen, and you react it with potassium hydroxide, which is a salt, we're going to do a deprotonation. We're going to end up with potassium ethoxide and water. Reversible reaction. The reaction actually lies to the left here because of the pKa differences. However, if we look at acetic acid, again with potassium hydroxide, we're going to get a reaction that allows us to form potassium acetate and water. And this time the reaction lies to the right because of the pKa differences. Now we need to draw these two reactions on an energy diagram. So we have the reaction coordinate on the x-axis, and we have energy on the y-axis. Now if we look at the reaction of ethanol plus potassium hydroxide, we're going to have a fairly high transition state energy. So we have our ethanol reacting with the potassium hydroxide, we have our transition state, and we have our products. And really I should be drawing this a little higher because the equilibrium lies to the left and not to the right. So these are kind of on the same, more or less the same energy as you might kind of predict, but this probably should be just a little bit higher. Now if I look at the acetic acid reacting with sodium hydroxide, or excuse me, potassium hydroxide, I'm going to go through a smaller transition state and the energy is actually going to be a little lower. And so that's what I really wanted you to identify, was that the transition states of these two reactions are actually quite different. And the products are actually quite different in terms of where they are with respect to their starting materials because of where the equilibrium lies. So you should have something that kind of looks like this. And for those of you who had 255 with me last semester, there was a J-Chem Ed article that I had you read on pKa. And this came directly from that article. And I'll try to put that in the Canvas shell for this semester, so you can go back and review that. But it's all about pKa, and you know that pKa is something that we really need to be paying an awful lot of attention to during our thinking about organic reactions. Let's look at question number, let's go to question number 5. So 3 and 4 you did fairly well on. That's just some review material. Here you just needed to know how to make the S configuration, and in question number 4 you needed to draw the two ethyl groups for trans 1,2-diethyl cyclohexane in a chair conformation that put them both in the equatorial position, not the axial position. Here we had a reaction where we're taking 2-methyl cyclohexene and we're going to react it with bromine in water. And I ask you to draw the product of that reaction. We know this is going to be a bromohydrin, and there's going to be some stereochemical issues that we need to take into account. So what happens is, if we think about the mechanism, this goes through a bromonium ion. And so my methyl group is going back, and now water will attack the most substituted carbon because it's the weakest bond in the bromonium ion. And ultimately we end up then with the methyl group coming towards us, the OH going back, and the bromine coming out in front. And so you needed to comment on why the alcohol group was on the most substituted carbon, and you also needed to make sure that you had the right stereochemistry. So the OH and the Br had to be trans to one another, and the methyl group and the bromine needed to be cis to one another. Now question 6 asks you to provide the product of the following reaction, indicate the reaction type, and provide a rationale for your choice. Well, the first thing that we should notice is that we've got a tertiary alkyl halide, and so no SN2 or E2 type chemistry can really occur here because of the tertiary nature and the fact that we don't have a strong nucleophile or a good base. So I know this is going to have to be either SN1 or E1 type chemistry, and both are possible. And so if we had an SN1 reaction, we would ultimately end up with a ether, and if we had E1 chemistry occurring, we'd end up at least with one type of alkene. So I'm going to decide to say that this is going to go primarily through an elimination reaction because we're at high temperature. And we know that these types of reactions at high temperature, the elimination is favored for the major product. And if we look at this particular alkyl halide, we recognize that we have 3 beta carbons. 2 betas that I have labeled the same thing, because if we eliminate the hydrogen here, we end up with the same product, and then beta prime. And so the major product that we're going to get is elimination, and we're going to end up with a mixture of these 2 alkenes. And you can't really predict which one of these is going to be the major product of the elimination, because both of them are tri-substituted alkenes. So you really needed to show both. And then you also needed to provide a clear rationale for your choice, which is what I just described. So you should have said something about the fact that we were at high temperature favoring elimination. You should have mentioned the fact that 2 alkenes were possible and that it was difficult to determine which one of those would be the major alkene. And by the major product here I meant was it the elimination of the substitution product. So you really didn't need to put down the substitution product as a product. Okay, let's talk a little bit about question 7. I'm not going to give all the details here, but basically you're reacting an alkyl halide with sodium cyanide, and in a reaction with water as the solvent, the student noticed that the reaction was slower than if they ran this in a polar aprotic solvent, in which everything was soluble. You needed to really explain this in terms of using illustrations and why the polar aprotic solvent allowed things to occur faster, and it's because of the cyanide. The nucleophile has a negative charge on the carbon. We've also got a lone pair of electrons with a neutral charge on the nitrogen. In a polar protic solvent, we have, like water, we have hydrogen bonding that occurs everywhere. And so if we think of making spheres and that can form these hydrogen bonds to the different groups, we know that we can do that. So these spheres I'm just going to use to represent a lot of water molecules that can be hydrogen bound to the nucleophile. And we know that hydrogen bonds are strong, and so that allows that anion to be strongly solvated, and so these water molecules are actually associated quite strongly. And so for these water molecules to get out of the way so that this can actually function as a nucleophile, you got to break a lot of fairly strong bonds, and that slows the reaction down. However, in a polar aprotic solvent, some of you use DMSO, some of you used acetone. It doesn't really matter. But in a polar aprotic solvent, like I'm going to just use acetone, and we will again use a circle to describe this. There are ion dipole interactions that are solvating this particular molecule. However, those ion dipole interactions are much weaker than the hydrogen bonds, and so this solvent can get out of the way a lot quicker and allow the reaction to occur faster. So you needed to have some type of diagram that showed the hydrogen bonding and the ion dipole bonding with an explanation of why one would speed up the reaction, whereas the other one would slow it down. If we look at question number 8, I asked you to draw the transition state between ethyl iodide and sodium azide. So if we take ethyl iodide and we react it with sodium azide, azide, remember, is N3-, it's a linear molecule. The reaction in our arrow pushing is an SN2 reaction where the nucleophile comes in from the back and the leaving group leaves, and we end up forming an alkyl azide plus sodium iodide as the byproduct. This is just the overall reaction. This is not the transition state. And so several of you just drew this and left it at that. This does not show you really what's going on in the transition state. The transition state is the structure where the nucleophile is coming in 180 degrees to the leaving group. And so if we think about N3- coming in and attacking that carbon atom, bearing the halogen, the leaving group has to be leaving. So we have a partial negative charge on the azide. It comes in with a full negative charge, but as it starts to form a bond, that charge starts to go away. The iodide in the alkyl iodide, the iodide is neutral in the starting material, but as the bond starts to break, it starts to take on a negative charge. And so we've also got attached to this, of course, another methyl group, and we've got two hydrogens, and I need to draw it with some proper perspective. And so we know it goes through kind of a trigonal planar around this carbon, just looking at these three groups. So it kind of looks like an sp2 hybridized carbon with two additional things on it. And this is what the transition state actually, we believe, looks like. And so the double dagger just means that it's the transition state structure. And so you can see as the nucleophile's coming in that it's actually pushing out the leaving group. Question 9 was taking 1-octene and doing the hydroboration oxidation reaction. So 1, 2, 3, 4, 5, 6, 7. There's 1-octene. And the hydroboration oxidation reaction, right, is BH3, THF, followed by hydrogen peroxide and base. And we end up generating the 1-octanol, so it's an anti-Markovnikov addition. You needed to talk about that, the fact that you got the 1-octanol as opposed to the 2-octanol. But you also needed to talk about the fact that the boron addition, the first step, right, results in a syn addition of the boron. 1, 2, 3, 4, 5, 6, 7, 8. And the hydrogen. They're added in a syn fashion to one another. And so when this gets oxidized off, the OH and the hydrogen are actually added in a syn fashion as well. And so although you can't really tell it in the product because it's acyclic, this is what's going on as well. So you needed to talk about the addition of the boron across the carbon-carbon double bond as being syn specific in that particular case. The last question was a roadmap. And so this is a review of all of your reactions, well, not all of your reactions, but a good number of your reactions that we started off with, or ended off with, I should say, in 255. And what you'll recognize is we don't know what we're starting with, but we're reacting it with bromine under light, and we're getting an alkyl bromide. This is an example of a free radical bromination of an alkane. And so starting off with that alkane, we can brominate that under free radical conditions to give the 2-bromo-butane. We then need to use some type of reagent to eliminate HBr. This is going to be a base. So we need a non-nucleophilic base that works well for this, something like DBU or DBN. Potassium tert-butoxide, I would have taken any of those. I would have even taken sodium hydroxide, would have eliminated to give the cisalkene, excuse me, the transalkene. This is the transalkene. And then we need to take this and go on and get a variety of other products. So we can go from an alkene back to an alkane that we started with. This is catalytic hydrogenation. But you need a catalyst for this. My favorite, of course, is palladium. But you could have put platinum or nickel. Any of those would have worked there and given you the product. I would have given you full credit for that. Taking this alkene to a Markovnikov alcohol. In this case, this is simply going to be water and sulfuric acid. We'll do this. You could have also done the oxymercuration demercuration sequence. I would have accepted that. Some of you put hydroboration oxidation, and that would have actually given us 1 butanol, which is not what we have here. We have 2 butanol, and so that wouldn't give you the correct answer. Taking this alkene and reacting it with chlorine, we're going to generate a dihalide, where the 2 chlorines are actually trans to one another. Remember, this goes through a 3-membered chloronium ion intermediate. You needed to take into account the fact that you're going to generate the trans stereochemistry. Many of you just drew single lines here without showing the wedges and the dashes, and so I had to count that wrong because stereochemistry is very, very important here. Here we have an example where we're taking an alkene and we're converting it into an alkyne. Number of carbons is the same, but obviously we're eliminating 2 more hydrogens to get to the alkyne. The only way that you know of how to do this is to actually halogenate it first. So for example, bromine, which is my favorite way to do it, to make the dibromide, followed by treatment with excess strong base like sodium amide. We'll actually do a double elimination to give you the alkyne. So you needed to show this as 2 steps. Some of you actually wrote Br2 and NaNH2 without signifying that these were done in separate steps, and that is not correct. If we mix the 2 things together, this won't work. Here we're reacting this with cold potassium permanganate. That's going to give us the syn addition of 2 alcohols across that carbon-carbon double bond. And again, very important that we show the stereochemistry here. And then here the treatment of this alkene with methanol in the presence of a catalytic amount of acid. This is going to generate an ether. And since it's with methanol, it's going to make a methyl ether that we have here. So this was just a refresher on some of the reactions that we studied in 255. Any of these that you might have difficulty remembering, go back in the book and look at your roadmaps that you built during 255. And you need to get these, all these reactions should be coming to you second nature now. So look at the handout that or the inverted lecture that I handed back with your feedback. Go over it, work these over again, make sure you understand the problems. And if you have any questions, stop by and see me during my office hours.